Welcome to the 5th lesson in the series on data representation in computers. In the previous lessons, we learned that text is represented in the computer as fixed-length binary codes, one code for each character in the text, and that numbers are represented using the binary numbering system. So far, we have only looked at whole numbers. By the end of this lesson, you should be able to explain the difference between the representation of integers and real numbers. Explain the concepts of overflow and underflow. Explain what rounding errors are. Salai, how tall are you?
Last time I checked, I was 1.54 meters.
1,54. How do we store that number in the computer? If we were to store it in an integer or whole number, we would lose the fractional part and Salai's height would be only 1 meter. As you can see, she's definitely taller than 1 meter, but not as tall as 2 meters. We need the fractional part. Instead of storing our height as an integer, we want to store it as a real number. A real number is a number that can have a fractional part.
Real numbers such as 234.55 and 0.043 are represented in floating point notation on a computer. It is important to remember that when you rewrite real numbers, you cannot change the value of the number. Floating point notation is similar to scientific notation. In scientific notation, all numbers are written as a value from 1 and less than 10. That is 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplied by a power of 10.
In other words, we only have a single digit before the comma multiplied by a power of 10. The only difference between scientific notation and floating point notation is that with floating point notation, we multiply by 2 by the power of 2 because we work with binary on a computer. Let's first investigate how to write decimal numbers in scientific notation and then apply what we learned to floating point notation.
Now see if you can follow the 4 steps in the 2 examples. And then once you understand, complete task 3.1 and 3.2.
2. Read the following steps and follow the examples to see how we write a number in scientific notation. Example 1. Write 234.55 in scientific notation.
Step 1. Place the comma so that only one digit is before the comma. We would get 2.3455.
Step 2. Moving the comma has caused you to divide the number, right? Now we have to make sure that we did not change the value. A movement of the comma to the left means that you have divided by 10 each time. So to make sure you have not changed the value, you must multiply by a power of 10. This means that we divided by 234.55 by 100 to look like 2.3455. So to keep the value the same, I need to multiply by 10 or 10 to the power of 2. Therefore, 234.55 in scientific notation is 2.3455 times 10 to the power of 2.
Step 3. When you divide by 100, you need to count how many places the comma has moved. This count will be the same as the exponent of the power you multiply by. In this example, we moved the comma 2 spaces, so we multiplied 2.3455 by the power of 10 with an exponent of 2.
Sure, we're nearly there. Step 4. Decide whether the power is positive or negative.
A positive power results when the comma moved to the left.
That's right. In the example, the comma moved 2 places to the left. So there was a positive 2 exponent, that is 2.3455 times 10 to the power of 2. Example 2. Write 0.234 in floating point notation. Step 1. Place the comma so that only one digit is before the comma. We get 2,34. Step 2. Moving the comma has caused you to multiply the number. Now we have to make sure that we did not change the value. A movement of the comma to the right means that you have multiplied by 10. So to make sure you have not changed the value, you must divide by a power of 10. So we get 2,34 divided by 10 or 2,34 divided by 10 to the power of 1.
Step 3. When you multiply by 10, you need to count how many places the comma has moved. This count will be the same as the exponent of the power you multiply by. In the example, we moved 1 space, so the exponent is 1. Step 4. Decide whether the power is positive or negative. Before you do this, remember that in scientific notation, a number is multiplied by a power of 10. This means that 2,34 divided by 10 to the power of 1 must be written as a number, 2,334. multiplied by 10 to some power of 1. So we get 2,34 times 10 to the power of -1.
The first question is simple. It's already written in scientific notation, so all we have to do is write 1,54 times 10 to the power of 0 in scientific notation. Here the exponent is 0 because we didn't have to move the comma at all. The diameter of a red blood cell is approximately 0,0075 millimeters. That is 7.5 thousandths of a millimeter. In scientific notation, that is 7,5 times 10 to the power -3 millimeter. Here the exponent is -3 because we had to move the comma 3 places to the right to get one digit before the comma. But remember, we don't want to change the value. We only want to write the number in scientific notation. If we move the comma 3 places to the right, we must also multiply by 10 to the power -3 to keep the value the same. We call the first part of each number in scientific notation the mantissa, and the power of 10 that it is raised to the exponent. Sometimes you'll see scientific notation written as the mantissa followed by an e and then the exponent leaving out times 10. You've probably seen this on some calculators. Floating point representation of real numbers in the computer is similar to scientific notation, except that the numbers are in the binary numbering system, not decimal. So, for example, the binary number 1011, 1101 base 2 would be written as 1,011101 base 2 times 2 to the power 3. We have the number being multiplied by 2 to the power of 3 because we moved the comma 3 places to the left. Here the mantissa is 1,0111101 base 2 and the exponent is 3, which in binary is 11 base 2. For a real number, a computer word is divided up into two main parts. One part to store the mantissa and one part to store the exponent, plus one bit for the sign, to indicate whether it is positive or negative of the number. For example, in a 32-bit word, one bit is used for the sign of the number, 0 for positive or 1 for negative, 8 bits for the exponent and 23 bits for the mantissa.
Sure, this is getting confusing.
Don't worry, it's not important to know the exact details of how the number is represented. What you do need to realize is that there is a limited number of bits for the mantissa and for the exponent. Using a 32-bit word like this, we can represent exponents from -45 to +38.
So if I have a number that is bigger than, let's say, 10 to the power 38, it wouldn't fit into a 32-bit word.
No, it won't. You would have to use a 64-bit word. Decimal numbers with exponents from -324 up to +308 can fit into a 64-bit word.
Wow, I can't even imagine a number that big.
Well, we don't normally need such big numbers, but supercomputers, for example, do. Supercomputers use a 64-bit word size or higher, and that enables them to work with very big numbers and with high accuracy. But remember, the mantissa is also limited. The 23 bits used for the mantissa in a 32-bit word means that the number can have 6 or 7 decimal digits in the mantissa. Have a look at your calculator. How many digits can it handle? Try entering 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 and repeat that again.
My calculator can only go up to 8, so the biggest whole number that my calculator can handle is 999999999. So if I were to try and add 1 to 9999999, it would give me an E for error.
Your calculator has what is called an 8-digit display. I can enter 1 and I can enter 0, but I can't enter 0,0000000005. When I try, it just takes the first 8 zeros and ignores the rest. When I multiply by 1,000, I get 0, not 0.000005. The number of digits that my calculator can display is limited, and in the same way, the mantissa of a real number is also limited when it has to fit into a computer word. The number of decimal digits that can be stored for the mantissa is called the number of significant digits. Significant meaning they make a difference to the number. As you saw, the extra digits you try to enter on your calculator are ignored. They are not significant. They don't make a difference to the number.
Well, I'd be quite happy working with 6 digits. I hate working with strings of numbers. I always make mistakes.
Yes, I'm also happy with 6, but sometimes scientists need to be more accurate than that. If they use a 64-bit word to store their numbers, they can have up to 15 significant digits, but it is still a limited number of digits. The accuracy or precision is limited.
Now I think I'm starting to understand. But why don't we just use real numbers? Why do we have to use integers? I mean, any whole number is just a number with comma 0 at the end, isn't it?
You're right. We could represent any integer as a real number with a fractional part 0. That's what your calculator does. So why does the computer have real numbers and integers? Much more complex circuits are needed for floating point calculations than for integer calculations. That means integer arithmetic is faster. Another reason is that with integer arithmetic, there are no rounding errors.
So what do you mean rounding errors?
Let's have a look at my calculator again. If I divide 1 by 3, I get 0.3333333. If I multiply by 3 again, I should get 1, shouldn't I? But I don't. I get 0.9999999. This is what we call a rounding error. It's the result of limited precision. This means that the number of significant digits that my calculator has is limited. Let's have a look at another rounding error. If I divide 4 by 7, I get a certain result. If I multiply that same result by 7 again, I should get 4, shouldn't I? But I don't. I get 3.9999995. It should be 4, but it's not exactly 4. If I round it off so that there are no decimal places, I do get 4.
Thank you. Now I understand what rounding errors are. But Dawn, at the beginning of the lesson, you spoke about underflow and overflow. What are those?
We'll pretend that we are limited to only 4 bits for representing numbers, just to make life easier for ourselves. Do you remember how many different combinations you can get with 4 bits?
16 combinations. Well, the largest number that can fit into 4 bits is 15, which is 8 plus 4 plus 2 plus 1. And if we also consider 0 as a combination, then that gives us 16.
That's right. We can remember it like this. 4 bits give us 2 to the power 4 combinations. 2 to the power 3 is 8. And so 2 to the power 4 is 16. But remember, half of the combinations are used for negative numbers, and the other half for positive numbers. The leftmost bit is a 0 for positive and a 1 for negative numbers. So from the 4 bits, we are left with only 3 bits for the magnitude or size of the number. So the numbers we can represent using only 4 bits are 0 through to 7 and -8 through to -1. 16 numbers in all. Let's say I have the value 7 in one group of 4 bits and the value 6 in another, and I want to add them. I should get 13. But 13 in binary is 1101. It has a 1 in the leftmost bit. So in our case of using only 4 bits, it will be seen as a negative number, which is the wrong answer. This is what we call overflow. We need 4 bits to represent 13, and we have only 3 bits available. Remember, one of our 4 bits is used for the sign. 13 is too big to fit into 3 bits. That's why we call it overflow. Overflow occurs when the result of a calculation is too big to fit into the word. The wrong result or answer is given as output. The same thing would happen if I try to multiply 7 and 6. I should get the answer 42. But again, that is too big to fit into 3 bits. The extra bit simply gets lost, and the 1 in the leftmost bit again tells us this is a negative number. Now, can you tell me, if a computer has a 16-bit word size, what is the biggest integer that can fit into a word?
2 to the power 16. No, 1 bit will be used for the sign, so 2 to the power 15, subtract 1, and that's 32,767.
Absolutely right. Now, let's say we want to calculate the number of seconds in a day. There are 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. So, we need to multiply 24 by 60 by 60. What does that give you?
That gives me 86,400.
Can you see? That number is already too big to fit into 16 bits. It would be better to have a word size of 32 bits. What's the largest value we could fit into a 32-bit word?
2 to the power of 31 minus 1, and that is 2147,483,647.
That's big enough for most of our normal calculations, but sometimes we need a word size of 64 bits if the numbers get really big. Of course, we always have real numbers to use as well.
Can you get overflow with real numbers as well?
Think about it. Could a number be too big to fit into a real number?
Yes, if I had an exponent greater than, what was it again? 38, for sure. That is a really big number.
Yes, if we are talking about positive exponents and 32-bit words. Can you think of an example when the exponent could get too big?
Yeah, if I had a number like 4 times 10 to the power of 38 and I multiplied that by 100 or even 1,000.
Yes, that would give us an overflow error. Can you guess now what an underflow error is?
An overflow is when a number is too big to fit into a word, and an underflow is when a number is too small.
Quite right. We usually see underflow when we multiply 2 very small numbers together and get a result of 0. Remember, the smallest exponent that we can have in a 32-bit floating point number is minus 45. If I multiply 5 times 10 to the power minus 45 by 10 to the power minus 5, the answer should be 5 times 10 to the power minus 50. However, minus 50 cannot fit into the number of bits provided for the exponent, so I end up with 0. This is the wrong answer. We call this an underflow error. Well, I think we've covered enough work for today. Decide for each of the following quantities whether you should use characters or text, integers or real numbers in the computer. Your address, your age in years only, your weight in kilograms, accurate to 2 decimal places, your telephone number, the number of days in a week, today's temperature, accurate to 1 decimal place. Give an example of a calculation that would result in overflow in a 32-bit word using integers. Give an example of a number in scientific notation that cannot be represented accurately if we pretend that only 2 digits are available for the mantissa. I hope you have enjoyed this series of lessons on data representation. When you start with spreadsheets, databases and programming, you will realize that it is important to choose the type of your data correctly. That is, whether you use text, integers or real numbers. I hope that then you will already understand the difference. Thank you for joining us. Till next time, goodbye.